Now we're going to take a look at a way of transforming triple integrals, again, over certain types of solids that will utilize the polar equations, but again, in a three-dimensional form, right? So that coordinate system, which is basically the 3D version of a polar coordinate system, is called the cylindrical coordinate system, right? And the word cylinder, you should kind of envision what your cylinder is, like a standard cylinder, like a can or something, where the cross section is a circle, and then, it goes up to a certain height. That type of solid is more easily described in this coordinate system as opposed to using our x, y, z. All right, so let's start with kind of a visualization of this. But the nice thing is we just get to build on what we did in 2D with the polar case. So let's start with our x, y, z space. I'm just going to give you a sense of the variables that we use and what those variables represent. So we know, for instance, this point here, let's say a certain x, certain y, and a certain z, right? So that point can be expressed in terms of our standard rectangular coordinates now, our x, our y, and z. Now, for the cylindrical coordinates, here's what we do. Instead of using x and y to represent the planar part of this ordered triple, meaning what's in the xy plane, we're going to switch your x and y over to r and theta, and we're going to keep the height, that kind of vertical variable, we're going to keep that the same. So the z won't change, it's just your x and y. So basically what happens now is, so that point that is in the sketch that I have here, that point that is directly below P, but in the XY plane, instead of using your X and Y here, we use R and theta. So the R is still going to be the distance from the point, or from the origin to the point, and our R is still going to be there. So this is theta measured from the positive x-axis. That is your R, and then you just go up z units, up or down depending on where you are, right? So if your z is positive, as we've seen, you're above the xy plane. If your z is negative, then you're below. Yeah, so this point now can be represented in this what we call cylindrical form. And the order is r, theta, and z. Now, because this is a triple integral, and again, anytime you're doing any kind of transformation in a multiple integral, Jacobians will come into play. At the very least, they'll tell you what formula, right, you're going to end up getting with this transformation. So if we write it down, so we know the relationship between x, y, and r and theta. Let's use those. So x is equal to r cosine theta. Y is r sine theta. And as we're saying, z will still be z. We're not changing that at all, right? It's going to be representing the same variable, or the same change, if you will. So the Jacobian for a 3D transformation, so in this case, our Jacobian, which will be in terms of r, theta, z, it's going to be this determinant. So I'm just going to write down the terms, but I'm going to say what each term represents. So in the first row, we're going to be differentiating the x equation. The x equation with respect to r is going to leave cosine theta. The x equation with respect to theta is going to leave negative r sine theta. Now we saw these previously, and now we just have to do a third derivative, partial derivative for x. But the nice thing is, because z is not a part of this equation, the partial derivative of this with respect to z is 0. We like that. If we do something similar for y, the partial derivative of y with respect to r, that's going to be sine theta. and then the partial derivative of y with respect to theta is going to be r cosine theta. Again, we saw these previously. And then the partial derivative of y with respect to z, no z, so this whole thing is treated as a constant. Its derivative is 0. Now when we get to the z equation, this z equation, there is no r, there is no theta. So if I differentiate this with respect to r, treating it as a constant, we get 0. And similarly with respect to theta, we get 0. And if I differentiate z with respect to z, I get 1. So that's what the determinant looks like, right, in the 3D case. And it turns out there are some other properties of determinants that say, hey, you can do expansion using other rows or columns. And it turns out, let's say we used a row or column that has a lot of zeros in it, the Jacobian, and this shouldn't surprise you, ends up being r. Right, the same r that we got in the polar case, because it's the same polar representation for x and y. We're just including z, but z is not affected by our r and theta. Right, so this is going to be our Jacobian. And let's just state it. Let's just state it so that we formally have our result, and then we'll do an example. So let's say, so here's our theorem. So this is the theorem where we're converting a triple integral from a rectangular coordinates, x, y, z, to cylindrical coordinates, r, theta, z. And here it is. So when you have your integral, now this is in some solid, but again, let's specify what coordinate system the solid is in. So in the x, y, z coordinate system, this is our solid. And then we have our function, which would be in terms of the same x, y, z. And then our volume, again, is our volume differential, also in terms of x, y, and z. Well, when we do this conversion, again, under certain assumptions of continuity and so forth, we'll be able to convert this to another triple integral over another solid. But now this solid will be in terms of r theta z. And then we will replace the x with the x equation, which is r cosine theta, the y with the y equation, which is r sine theta, and then the z stays the same, so no change for z, it's still z. And then the differential now will be some expression of, oh, I can't forget the r, I gotta put my r in there, and then times the absolute value of my Jacobian. But our assumption that r is greater than or equal to 0 means I don't need the absolute value, and it's r, and then you have your volume differential in terms of r theta v. And the typical order in which to do this is dz, dr, d theta. But if it turns out, for instance, that you have some kind of triple integral where all the limits are constant, then we know by Fubini that we can integrate in lots of different ways. In fact, 6 different ways, as we've seen previously. All right. So that's our formula. So let's take a look at an example of this. And since the word cylindrical is in the name of this process, maybe we should, just for fun, integrate over a cylinder. So let's do our example. And so let's say we are going to integrate just x. Let's say we're going to integrate, let's say our function is just x, and then this is dv over s, and then let's describe what s is. So where s is the cylinder, and this is centered at the origin of radius, let's say radius 2, centered at the origin, and then let's say with the base at z equals 0, so that's our xy plane, and height z equals 4. All right, so that's what we're doing. And you can interpret this as us finding. So let's say the density of the cylinder is just the function x, right? That's simple density. Just the density is equal to x. And if we're integrating the density, we know that gives us the mass. So basically, we're finding the mass of this cylinder. All right. Well, let's see if we can sketch this. Again, it's 3D, so it might be a little bit harder. So let's see what this would look like. So there's our standard X, Y, Z space. And we know, where's my Z? There it is. So it said that the base is at Z equals 0. So it's in the XY plane. And then the radius is 2, so it's just going to go out, 2 units all around. Now, let me kind of do the negative x-axis. Let me do the negative y-axis. I don't need the negative z-axis because, again, the base is at z equals 0, and then it goes up to z equals 4. So let's say 1, 2, 3, 4. So all you do is, for the base, and again, it's a little challenging, but for the base, let's just draw a circle, and with no other information in the question, we're going to assume that this is a full cylinder as opposed to like a half cylinder. You have those kind of cylindrical wedges. But let's just do this going all the way around. And then basically translate that 4 units up to get the height, the top of this cylinder. So again, not perfect by any means. And then let's add the edges of our cylinder, and it looks kind of like that. All right? Right. But then it's all filled in, because remember, it's a solid, right? This is a solid. It's like a cylindrical block of wood as opposed to an empty canister. And we're integrating over everything here, right? So let's see if we can write down the limits, right? So in terms, and we need the limits for r, for theta, and z. So let's start for r. Because it's the full cylinder, the radius ranges for, and I should say all the points in and on the cylinder, the radius ranges from 0 to 2, right? So that's our limits for r. So r is between 0 and 2. Theta, again, because we do it's one full cylinder, that's one full revolution, so our theta is going to be 0 to 2 pi. We like that. And then, because the base of the cylinder is at z equals 0, so it's in the xy plane, and then this, the height is in the plane 4 units above that, right? So then your z goes from 0 to 4. And those are our limits, all right? Okay, so we have our limits there. Now, this function just has x, right? It doesn't have anything like x squared plus y squared. But remember, we have an equation just for x. So we know that x is r cosine theta. So that's going to be our function. So here, in some sense, you could say, because of the simplicity of the function in terms of x, when we convert it to the cylindrical form, it gets a little bit more complicated, because now we have r and we have theta. But still, these are functions that are not terribly difficult to integrate. So we have our limits, we have our function. We know what our Jacobian is. It's going to be r. Let me write it down. So the Jacobian, in terms of r, theta, and z, it's just going to be r. And then I'm going to choose, so let me go ahead and set up the triple integral now and evaluate it. So we got, doesn't look good, so let's go. So here are 3 integrals. I like to use, especially when the limits are constant, you can choose whatever order you like, but let's put the Jacobian in, so it's going to be r. And then I just like to do dz, dr, d theta, right? And then now let's put our function in. So our function is r cosine theta. So we have that. And then based on my order, I'm going to first do 0 to 4. And then r is from 0 to 2, so that's going to be my second integral, and then theta is 0 to 2 pi. All right, and there's our triple integral. Now, the nice thing about this is that it's separable. Like we can, one factor in terms of r is r squared. The other factor in terms of theta is just cosine of theta. And for z, you can think of it as a 1 because there's no z in this function at all. So this one is separable, and because the limits are constant, we can use that property. And instead of having one big triple integral, we can multiply 3 separate single integrals. So let's do this. So let me do the dz first. Well, that's going to be 1, and then it's going to be dz, and then z goes from 0 to 4, so we have that. And then times, let's do the integral with respect to r. That when we factor out the r squared, we'll have a factor of r squared, and r goes from 0 to 2, and then that's dr. And then times the integral with respect to theta, we'll have 0 to 2 pi, and then we'll have cosine of theta. So cosine of theta d theta, right? So not every problem is going to end up like this, where we can somehow use the separability of the function with coupled with Fubini's theorem, order doesn't matter, all that stuff. So we will have z, so the antiderivative of 1 with respect to z is z, and that goes from 0 to 4. The antiderivative of r squared with respect to r is 1/3 r cubed from 0 to 2. And then the antiderivative of cosine is sine. So sine of theta from 0 to 2 pi. Now we get to use our FTC for each of these. So let's go down. So at the upper limit for z, so we just have 4 minus 0, right? That's upper minus lower. And then for r, we end up having, let's see, 8/3 minus 0. And then with the sine function, this is kind of interesting now because the sine of 2 pi is 0. And the the sine of 0 is 0. So we end up having this. It's like, whoa, because, so this ends up being 0. So what does this mean? Well, it just means that there is some kind of symmetry in terms of the cylinder where I guess you could think of this as like a net mass, right? And it comes out to be 0. But more than the physical interpretation, we want to focus. We want to really focus on the process of doing the transformation. And the cylindrical coordinate system, it doesn't only work well just for cylinders, but anything, again, where you have like a circular boundary, typically in terms of x and y, or I should say a certain pair of variables, right? So it's kind of, this cylinder is circular in terms of x and y, but then it's linear in terms of z because it just goes straight up. Representing that kind of solid in a cylindrical coordinate system often makes your integrals a little bit easier. All right, so hopefully you found that interesting, and we have another type of transformation coming up in the next video where we're going to introduce what's called a spherical coordinate system. So I know you can't wait to see that. I'll see you in the next video.